All right, welcome to The Explainer. Today we're going to tackle a question that, well, it seems to break the rules of reality every single time you look out an airplane window.
I mean, really think about it. How does a 400-ton machine, this giant metal tube, just defy gravity? It's wild. And the answer, well, it's kind of simple, but also incredibly deep. So to figure this out, we can't just look at the plane's engines. Nope, we have to start with the invisible ocean we're all swimming in right now, the air. See, flying isn't about brute force. It's about understanding and, really, working with the air. Okay, let's dive right in. The air around us. Now, we tend to think of air as just empty space, right? But it's not. It is a real physical thing. It has weight, it takes up space. Seriously, it behaves just like the water in an ocean. I mean, look at this. It's mostly nitrogen and oxygen with a little bit of other stuff mixed in. But the key thing is, all those gases have mass. They have weight. And this massive blanket of air surrounding the entire planet is constantly pressing down on everything. And that constant pushing, that's what we call atmospheric pressure. Get this, at sea level, it's about 14.7 pounds pushing on every single square inch. Imagine balancing a bowling ball on the tip of your finger. Now imagine that force all over your body. That's what we're dealing with, all the time. Okay, and this is where it starts to get really interesting for flight. As you go up, as your altitude increases, that pressure just falls off a cliff. Look at that. By 18,000 feet, you've only got half the pressure you have at sea level. That difference, that change in pressure, that is a huge piece of the puzzle. So we've established that air is a real substance with real pressure. But how does it behave? How does it act when something, say like a wing, tries to move through it? Well, the secret is that air acts like a fluid. Yep, just like water or even honey, air has this property called viscosity. It's basically a measure of its internal stickiness. Now, air isn't thick and goopy like honey, obviously. It's much more like water. It flows super easily. But that little bit of stickiness, it's still there, and it matters. And then there's good old friction. The same force that resists you when you slide something across a table. When a wing slices through the air, that friction makes the very first layer of air molecules cling right to the wing's surface. It creates this super thin skin of air that moves with the wing, called a boundary layer. Okay, stickiness, friction, why are we talking about this stuff? Because it all plays into one of the most critical factors for flight, air density. Basically how thick or thin the air is. And a bunch of things can make the air thinner or less dense. Pilots have a term for this, high-density altitude. Going up higher is the obvious one, sure, but so are high temperatures. And, here's a cool one, high humidity. You'd think wet air would be heavier, right? Nope, water vapor is actually lighter than dry air. Wild. And this is the big challenge. When the air is thinner, it means there are just fewer air molecules packed into the same space. So the engines have less oxygen to burn for power, the propellers have less stuff to bite into and push, and you guessed it, the wings have less air to work with to create that all-important lift. Okay, quick recap. Air is a fluid, it has pressure, it has density, we have all the ingredients. Now let's finally put them together and see how a wing performs the magic trick of creating lift. And it turns out there are two main ways to look at this, thanks to two absolute geniuses, Isaac Newton and Daniel Bernoulli. It's not that one is right and the other is wrong, they're two sides of the same coin. You can think of it as Newton giving us the push from under the wing and Bernoulli giving us the pull from over the wing. Let's start with Newton, his third law of motion. You've heard it a million times. For every action, there is an equal and opposite reaction. Simple, right? You push on a wall, the wall pushes back on you. So how does that work for a wing? Well, a wing is basically a giant, cleverly shaped air scoop. It's angled to grab a huge amount of air and force it downwards. That's the action. And the reaction? The air pushes the wing upwards. And that, my friends, is lift. It's that simple, on one level. But wait, that's not the whole story. Enter Bernoulli's principle. This one's a little less intuitive, but it is just as powerful. And the core idea is this. For any fluid, whether it's air or water, the faster it moves, the lower its internal pressure becomes. Faster flow, lower pressure. Remember that.
The perfect way to see this in action is with something called a Venturi tube. Okay, look what's happening here. Air flows in at a normal speed and pressure. Then it hits this narrow section, this bottleneck. To get the same amount of air through that smaller space, it has to speed up. And what happens when it speeds up? Bam! The pressure drops dramatically. This little effect is the secret sauce for the other half of lift. Okay, so we have Newton's push and Bernoulli's pressure drop. How does a simple wing use both of these ideas? It all comes down to its very specific, very engineered shape. It's called an airfoil.
The absolute genius of the airfoil is that it's not symmetrical. See how the top surface is more curved than the bottom? That longer, curved path forces the air that goes over the top to travel a longer distance in the same amount of time. And to do that, it has to move faster, way faster than the air taking the shortcut underneath.
And what did we just learn from Bernoulli? Faster air equals lower pressure. So now you have this zone of low pressure on top of the wing and a zone of relatively higher pressure underneath. That pressure difference creates an undeniable upward force. So the wing is being pushed up from the bottom by high pressure, and at the very same time, it's being sucked up from the top into that low pressure zone. That's lift.
So there you have it. You've got Newton's action-reaction, pushing air down to go up, and you've got Bernoulli's pressure difference creating this incredible suction force. They work together. But there's one more little detail, a little bit of chaos that happens right at the tips of the wings. Think about it. You've got high pressure on the bottom and low pressure on top. What's going to happen at the edge where they meet? Well, nature tries to balance things out. That high-pressure air tries to sneak around the wingtip to get to the low-pressure area on top. And when it does that, it creates this swirling tornado-like vortex of air that spins off behind the plane.
Now, engineers have gotten really smart about managing these vortices. You know those little fins that curve up at the end of a plane's wings? That's what those are for. It's all part of this beautiful, complex dance with the air. So we figured out how a plane flies. It's this elegant mix of pushing air down and creating pressure differences. But all of this works beautifully when you're moving through the air. What happens when you start moving so fast you literally break the sound barrier? When all these neat rules of flow kind of get thrown out the window? Well, that's a whole other explainer.